Okay, welcome everybody. So far we have been thinking about vector spaces, and then we defined what it means to be a subspace of a vector space. So in the next set of videos, I want to take a look at some really special subspaces of vector spaces that we can imagine from matrices. So in particular, let's consider an m by n matrix A. So this matrix A we can think of as a map from Rn into Rm. Since this matrix A we can multiply by vectors, and in order for that product to make sense, this vector that we multiply by matrix A, that has to have n different rows. So x is in Rn, and after multiplying A by this matrix, we wind up with some object over here, which is going to be in Rm. So I can think of a matrix, as we've been doing before, as a map, as a transformation from Rn into Rm. And looking at some important pieces of this map, we can construct some subspaces either of the domain Rn or of the codomain Rm. So the first subspace I want to take a look at is what's called the null space of this matrix A. And we use the notation NUL, we cut off one L, to denote the null space of some matrix A. And by definition, this is going to be the set of all vectors x, okay, which sit in Rn in the domain, such that when we multiply matrix A by this vector x, we get the 0 vector, which is in the codomain in Rm. So in other words, the null space of matrix A is the set of all vectors in the domain of A who have an image that gets mapped to the 0 vector. So we're trying to identify what are all vectors x in the domain whose image is equal to the 0 vector in the codomain. And so just revisiting this homogeneous matrix equation, recall Ax equals 0 is always going to have a trivial solution. So x equals 0, the 0 vector, is always going to be one such vector in the null space, but there may exist other vectors that get mapped to the 0 vector if the solution to the homogeneous matrix equation is not unique, if they're non-trivial solutions. So let's take a look at an example. So let's consider the following matrix A. So A has, in this case, we've got 2 rows and 1, 2, 3, 4, 5 columns. So A is a 2 by 5 matrix. So in particular, this would tell us that A, for example, is a map from R5 into R2. I can apply matrix A to a column vector that has 5 entries, and after I calculate that product, I'll wind up with a vector that's in R2. So we would say that the domain associated to this map is R5, which is the number of columns in matrix A, and the codomain is R2, which is the number of rows that matrix A has. So we can think of the domain and the codomain as vector spaces where we're using the usual vector addition and scalar multiplication. And so now let's consider what would the null space of this matrix A be? Well, we need to consider solutions of the homogeneous equation Ax equals 0. And what's a useful step to solve this matrix equation, Ax is equal to the 0 vector, would be to work with the matrix and find the reduced row echelon form of this matrix, recall, and from that reduced row echelon form, we're able to generate the solution set. So by applying some operations, row operations, or by using Python, and I'll put a link to a Google Colab notebook below in the description of this video that calculates the reduced row echelon form of this matrix, you can verify that matrix A is row equivalent to this reduced row echelon form, where the top row is 1, 2, 0, 13, 33, and the second row is 0, 0, 1, minus 6, minus 15. And so what's important to note here is we have two pivot entries. I have a pivot here in column 1. There's no pivot in column 2. And then I have a second pivot in column 3. And there's no pivots in column 4 or column 5. So from this, I can see that x2, x4, and x5 are free variables, since those columns don't have a pivot. And from the pivots, we can see that the solution to the homogeneous equation, for example, would be that x1 is equal to, and then we would need to bring all of these terms to the other side of the equation if I wanted to solve for x1. And that means this would look like minus 2 times x2 minus 13 times x4 minus 33 times x5. And we can solve for x3. We have a pivot in the third column, and this would look like 6x4 plus 15x5. So this would be our solution set. And as we've seen, it is useful to write this out in vector form. So I can write this solution as the vector x is going to equal, and then I can think about this as x2 times a vector. So in this case, the x1 position has an x2 there. x2 is equal to itself, and x3, 4, and 5 are independent of that. And then the next free variable is x4, and that appears in x1, not in x2. It appears in x3. Here's the position for x4, and then we have a 0. And then lastly, we have x5 times minus 33, 0, 15, 0, and 1. So here I've just written out the homogeneous solution set in its vector form. So the null space of A is going to be the set of all vectors that look like this. So I can express this set as the set of vectors spanned by these three vectors that we have over here. So therefore, we see that the null space of matrix A, therefore, we can write as the set spanned by the following three vectors. The first vector is minus 2, 1, 0, 0, 0. The second vector is minus 13, 0, 6, 1, 0. And the third vector is minus 33, 0, 15, 0, 1. So any vector that gets mapped to the 0 vector under this map defined by matrix A has to be a linear combination of these three vectors. And any vector that is a linear combination of these three vectors is definitely going to get, after it's multiplied by matrix A, it will have an image which is the 0 vector. So here we've got the null space for matrix A.